Hi everybody, my name is Zach Alexander, and I'm presenting on Project 2 for our CUNY Data 620 Web Analytics course in the summer 2020 semester. My group members are Misha Kollontai, Amber Ferger, and Suba Rao. The instructions for this project were one, to identify a large two-mode or bipartite network dataset, reduce the size of the network using a method such as the island method described in Chapter 4 of our textbook, and then make some inferences based on the distinct groups and subnetworks that resulted from using the island method. For our Project 2 assignment, we decided to take a look at a bipartite network of 40 composers of film scores and the 62 producers that produced a minimum of 5 movies in Hollywood from 1964 to 1976. For this network, each node represents a composer or producer, and an edge or line between a composer and producer indicates the composer created the soundtrack for the movie that was produced by the producer. Additionally, there was one edge attribute, which denotes the number of films that were collaborated on between a producer and composer duo. The aim of our project was to do a couple things. One, we wanted to load our bipartite network into a Jupyter Notebook successfully, then use the island method outlined in our textbook to subset our larger network, and we used the edge weight, again being the number of collaborations between a producer-composer duo, to kind of create separate islands. And then finally, with this higher water level and these islands that have been created from our larger network, we wanted to do a couple of things. One, we wanted to explore whether or not certain subnetworks showed higher productivity than others, and productivity being the number of films that were collaborated on between each other. And two, whether or not our subgroups worked more in isolation or typically collaborated with the broader bipartite network of producers and composers. Initially, we had to load our dataset into R since it was only available as an R data file. Then, after doing a bit of manipulation in R, we exported each component as text files and read these text files into our Jupyter Notebook. The components consisted of our list of composers, our list of producers, and our interaction matrix between our composer-producer nodes. We then created a function to properly map our producers and composers to the proper rows and columns of our interaction matrix. This took a bit of time, but in the end, we were able to generate a bipartite graph. Once it was loaded in, we could identify some basic characteristics. As we can see, there were 101 nodes and 192 edges. The average degree is quite small for this network at a value around 4. And we will go into more detail about this later, but we can see from this that there's not a high degree of connections between our nodes relative to other datasets that we worked with in the past, such as our school study network that we used in Project 1, which showed a much higher average degree connectedness between students and their peers. We can indeed see that this graph is bipartite after we've loaded it in successfully. And as a reminder, we have an edge attribute, which is the number of collaborations on soundtracks between composers and their connected producer. And this is an example here. We can see the edge of Rosenberg A and Goldsmith J. There were 3 collaborations between these two nodes. With some basic characteristics determined of our large network, we decided to do a quick visualization, and first in a circular format here. We colored the nodes blue for producers and red for composers. And then we also did this in a bipartite layout here. Again, coloration is the same of our nodes, but we can see very distinctly that there's a varying degree of collaborations between composers and producers, and that's apparent by the thickness of the edges. We can also see too that there's a few very thick lines, meaning a lot of collaborations between a duo, but then there's a lot of skinny lines here, suggesting there are a lot of one-off collaborations between a producer and a composer. Because of this, we thought it was a good opportunity then to use the island method, using our edge weight, to raise the water level a bit to create some islands of our larger network. In order to do this, we needed to isolate our weight edge attributes and find the nodes and their corresponding edges that have weights at a certain threshold and determine the threshold we thought was most necessary for our island subset. As we can see from our custom function, Here, if we were to remove all edges with a weight of one collaboration between a composer and producer, we would have 71 nodes remaining and 15 distinct islands. If we took another step and removed all edges with weights of 1 or 2 collaborations, we'd only have 34 nodes remaining and still have 14 distinct islands. Because of this, we thought it would be a good threshold to use an edge weight of 1 in order to preserve a larger subnetwork of nodes for further analysis. After saving the subnetwork in a new graph object, we then were able to display it here. And you can see very distinctly the 15 different islands that we've created. Now that our graph has been subset into distinct islands, we can further explore the connections of these islands. First, we thought it would be interesting to create a custom function that would traverse our nodes starting at each node and measuring the number of nodes that make up each producer-composer's immediate network with a radius of 2, which is this function here. We then save these values in a data frame and show the top 4 producers, composers with the most connections in their immediate networks. We can see that Schartoff, Winkler, Wallace, and Jacobs, who are all producers, have pretty large networks, and one composer, Jay Goldsmith, also rounds out the top 4. We also display these 4 subnetworks in a bipartite layout here, where it's interesting to see that both Schartoff, Winkler, and Jacobs, 2 of the top producers, have collaborated with Jay Goldsmith, our top composer. With our radius set at 2 here, we can see that Jay Goldsmith's connections to other producers directly affect Schartoff, Winkler, and Jacobs' immediate networks as well. You can see here the connection with Schartoff, Winkler with Goldsmith, and same thing with Jacobs here. The connection creates a pretty large impact. As we can see from our initial visualization of our 15 islands, there was one fairly large subnetwork. I'll show you here, and it's this one right here. In order to capture all the nodes of this large subnetwork and do some analysis on it, we created a custom function that started at a central node. We used Schartoff-Winkler's node in this case because it was quite central in the subnetwork, and traversed the connections based on iterating the number of radii to expand outward to. As we can see from our printout, that when we reached a radius of 8, we had successfully captured all the nodes in the subnetwork. With this subnetwork stored now in a new graph object, we displayed it below here. Again, being 8 is the radius when we captured all the nodes, we then were able to display it here. With our isolated subnetwork ready to go, we then ran some centrality measures on the subgraph to identify a degree centrality and between the centrality of each node. What we found was interesting. Jay Goldsmith had the highest degree centrality value in the subnetwork, but when we dove a bit deeper, it was important to note that he collaborated with 3 producers that nobody else collaborated with, at least twice. So meaning that we would expect that his degree centrality measure would be quite high, but not necessarily a high between his centrality value. When we look at the table sorted by between his centrality, this is indeed true, showing that only one node from the first table sorted by the top degree centrality values makes it into the top between his centrality values, and that's Schartoff-Winkler. Because Schartoff-Winkler's degree centrality value was lower due to him being tied to only a small number of nodes, we can see from a between his centrality perspective that he clearly holds the entire cluster together, whereas Node ties together 3 subgroupings of the cluster through his collaborations with Jones, Fielding, and Goldsmith. There's no surprises between his centrality value is the highest. And we can also see this visually too. Schartoff-Winkler and his connections with these 3 nodes. Additionally, it's interesting to note that there weren't any loops in this subnetwork. In that, at least at our threshold of 2 interactions, very few individuals repeatedly worked with more than 2 people. We can see here, when we look at the edge weights here, that only 8 of the 31 nodes in the subnetwork had more than 2 repeated collaborations. Looking at a few smaller subgraphs or smaller islands that we created from our larger network, for instance, one that was pretty interesting was involving Jay Williams, a producer who collaborated with 5 different composers on films between our denoted time period. And you can see here that he's a central node, but collaborating with 5 different composers on his films. Another interesting subgraph was this one right here, where we saw a higher average number of collaborations than some of the other subgraphs we explored. And it was driven mostly by this tight-knit quad of Baker, Anderson, Miller, and Brunner here. But you can see the average is much higher, 3.7, whereas some of the averages that we saw of our edge weights were in the 2.5 range. So in the end, we examined a complicated network of producers and composers and their collaborations on movie scores. It was interesting to see that based on our threshold of subsetting by at least 2 collaborations, we saw a large amount of 2 or 3 person networks pop up, and only 3 networks consisting of more than 5 individuals. Additionally, we noticed that it was very rare for a composer and producer to work together more than 2 times. This was especially relevant in our largest subnetwork of our 15 islands. While utilizing the island method to subset our larger network, if we were to progress with our threshold of subsetting the network to only include collaborations above 2, the number of islands would have only decreased from 15 to 14. However, the number of nodes would have dropped by almost 50%, down to about 30 or so. This indicates that all but one of our small networks contain at least one interaction of at least 3 collaborations, and that these smaller subsets tend to be very tight-knit pairs that stem from successful producer-composer partnerships. When looking at the summary breakdown a bit, go back up to here. Our largest subgraph generated by our island method contained a maximum connection weight of 4, despite the highest weight in the overall network being 8. 2 additional pairs collaborating together 7 times, and an additional pair collaborating 6 times. None of these pairings were in the 3 larger subgraphs that we examined, further suggesting that several incredibly tight and productive partnerships developed, and they rarely seemed to branch out. For our movie scores network, the one large central network of people that were collaborating seemed to be something more of a product of random connections, especially given that there weren't more loops where producers recommended composers for collaboration with their colleagues and vice versa. Instead, we saw that the true network was really quite small, and that individual pairs were quite productive and happy working together on multiple scores together, but they worked more so in isolation and didn't really branch out too much. And that's pretty much it. Thank you.